So in this last of our discussion on series, we will be discussing the root test, and then we will do Leibniz theorem and just introduce what is the meaning of absolute convergence. Okay, so in the beginning, let us look at what is Cauchy's root test. Suppose you are given any series summation an, and let mu be equal to the lim sup of nth root of mod an. So this does make sense, because if you take any real number an, then modulus of an is a positive or at least non-negative number. So you can talk about its nth root, and the result is telling you that if mu is less than 1, then summation an is convergent, and if mu is greater than 1, then summation an is divergent. So let us first prove this result in its generality, and then we will make a few remarks, as in the case of ratio test, as to the specific situations which may arise. Okay, so the first part is that suppose your mu is less than 1, then you wish to prove that the series converges. Okay, so since mu is less than 1, you can always choose a real number beta, so that mu less than beta less than 1, right? And we are going to use this beta to get a nice geometric series. How do we do that? Now, since mu is the lim sup of nth root of modulus an, by definition, or rather by a equivalent characterization, there is a positive integer n, so that the nth root of mod an will be less than or equal to beta after the capital nth term. So for all little n greater than equal to capital N, you will get nth root of mod an will be less than or equal to beta. So now you just take the nth power of this inequality. What do you get? That mod an is less than or equal to beta to the power n for all little n greater than equal to capital N. And what do you know about the series summation n equal to 0 to infinity beta to the power n? This series is convergent because beta is less than 1. This is just the geometric series, right? So if you want to be very careful, again, actually I have discussed this during the comparison test, so I don't need to stress it so much here, that it is, even if it happens after a certain term, this implies that summation n equal to 1 to infinity an is convergent, right? Because it is being dominated by a convergent series, so therefore it will be convergent. Okay. Similarly, if you let your mu to be greater than 1, that is lim sup of nth root of mod an, if it is greater than 1, then you have to show that the series summation an diverges. So again, since mu is greater than 1, nth root of mod an will be greater than 1 for infinitely many values of n, right? The characterization of lim sup gives you these two properties. One of them you have used here, the second you are using it here. That for infinitely many values of n, nth root of mod an will be greater than 1. So what does that mean? That for infinitely many values of n, mod an will be greater than 1. So mod an is greater than 1 means that an for these infinitely many values of n will either be greater than 1 or less than minus 1, right? So if you get infinitely many values of an which are either greater than 1 or which are less than minus 1, then what can you expect? You can expect that either the series will be a not series, I'm sorry, the sequence an or sequence mod an, if you like, will either be a divergent sequence, or even if it converges, then it will converge to a number which is greater than equal to 1, right? So even if you don't want to talk about the sequence an straight away, if you look at the sequence mod an, then infinitely many values of n uh, are such so that mod an is greater than 1, which implies that either the sequence mod an is going to be divergent, or even if it is convergent, then its limit will be greater than equal to 1, right? So, because it's at least one cluster point will be greater than equal to 1. I hope I have made myself clear. So therefore, because infinite, let me just stress on this, since infinitely many values of n are such that mod an is greater than 1, you will be getting at least one subsequence of mod an, which is all of whose terms are greater than 1. So for that subsequence, at least the limit is going to be greater than equal to 1. So if the original sequence converges, then it has to converge to that number which is greater than equal to 1, or in the other case, it may diverge also. So whatever, the basic thing is that you will never have this situation that mod an is a null sequence. So whatever happens, limit n tending to infinity mod an cannot be 0. Since it cannot, limit of n tending to infinity mod an cannot be 0, so therefore an cannot be a null sequence, because we know that an is a null sequence implies mod an is a null sequence. And therefore what have you got from a result which we proved in the previous lecture, that your series cannot converge, because summation an converges implies that if you look at the sequence of its terms, that is summation an converges implies limit n tending to infinity an equal to 0. So therefore, once you have assured that limit n tending to infinity an is not 0, you can say that the series cannot converge and hence it is divergent. So that is your result, that you look at nth root of mod an and this sequence and look at the lim sup of that. Then if it is less than 1, then summation an converges, and if it is greater than 1, then summation an diverges. Okay. So again, we will look at some special cases. So first of all, if all of your ANs are greater than equal to 0, then the second statement that summation an diverges can be qualified to say that summation an is properly divergent to infinity. Because if all the ANs are greater than equal to 0, then your corresponding sequence of partial sums is a monotonically increasing sequence. So since it is a monotonically increasing sequence, there are only two possibilities. Either that it is going to converge to a limit, or it is going to be divergent. So corresponding series is also either going to converge or it is going to be properly divergent to infinity, and therefore you can make this remark. Secondly, if your limit itself exists, limit n tending to infinity nth root of mod an exists, then obviously that is going to be equal to the lim sup of nth root of mod an. So therefore you can state the test in terms of the limit. That is, if the limit is less than 1, then your series will converge, and if the limit is greater than 1, then the series will diverge. Okay, and finally, as in the case of ratio test, if your limit is equal to 1, then you cannot make any conclusions. The test is inconclusive. So again, the example which I am taking is the same example. Look at the series, harmonic series, summation n equal to 1 to infinity, 1 by n, and the series summation n equal to 1 to infinity, 1 by n squared. Then we know that the limit n tending to infinity, nth root of n, that is equal to 1, right? So that will imply that limit n tending to infinity, nth root of 1 by n, that will be 1, and limit nth root of infinity, 1 by n, sorry, limit n tending to infinity, nth root of 1 by n squared, that will also be equal to 1, right? Because we know that limit n tending to infinity, nth root of n is equal to 1. So let me just try something which I have just learned. So what I'm trying to say is that limit n tending to infinity, nth root of n. This we have seen that this is equal to 1, right? So I'm using this fact to claim that if I look at the nth term here, and if I apply the nth root of an and look at the limit as n tends to infinity, then that will be 1, and similarly for this one. Because it will just become 2 by n, so that it is the same thing. You can just find out limit nth root of n and then take the squared of that, right? So you're still going to get 1. So these two limits, for both these limits, your mu is equal to 1. But now what you know that the harmonic series diverges to infinity, whereas the series summation n equal to 1 to infinity 1 by n squared, that converges, right? So let us just go to the next slide now. Yeah. So as an example, let us look at this. That suppose I have two numbers, real numbers, a and b, and they have this relation a less than b less than 1. Okay. So then you look at the series summation an, where the odd terms are a to the power n and the even terms are b to the power n. Okay. So how does the series look like? It starts with a, then you add a b to it. So a plus b plus a squared plus b squared plus a cube plus b cube plus etc. Right? So in this series, suppose I am trying to apply my root test. So I have to find out what is nth root of n, an, and as n tends to infinity, I want to find out the limit of this if possible. And if not, then at least I want to find out the lim sup of nth root of an. Here ans are all positive, so I don't have to talk about mod an. Okay, so since the series terms are dependent on what term you're taking, if it is an odd term, it looks like something, and if it is an even term, then it looks like something else. So let us do the computation for the even term and odd term separately, first of all. So what is your uh, 2nth square root of the 2nth term, right? So the 2nth term is b to the power n. So if you do b to the power n whole to the power 1 by 2n, what will you get? You'll just get square root of b, right? B to the power n divided by 2n, so n cancels out. Only thing is left out as root b. So therefore, the 2nth root of the 2nth term is square root of b, right? And what is the 2n minus 1th root of a 2n minus 1? That will again be a to the power n divided by 2n minus 1, right? And so if you just write it in this fashion, it just becomes 2 minus 1 by n inverse, right? So just check whether it is the same thing or not. 2n minus 1 divided by n, and inverse means n goes in the numerator and 2n minus 1 goes in the denominator. So 2n minus 1th root of a 2n minus 1 is equal to a to the power 2 minus 1 by n inverse. So if we take we see that if we look at the subsequence of this sequence consisting only of the odd terms, and if we take the limit there, that will exist, and that will be equal to what? Root a. Because if you're taking the limit as n tends to infinity, then this 1 by n becomes 0. So all you're left with 2 inverse. So a to the power 2 inverse means a to the power half. So that is equal to square root of a. So if you look at the subsequence of this uh, sequence which is forming the series, the even terms subsequence is a constant sequence taking the value root b, right? So if you take the limit, you will get root b, and the odd sequence, subsequence, sorry, if you take, that is also convergent, and its limit is square root of a. So what is going to be the lim sup? Lim sup is going to be the maximum of these two, so that is root b. right? Why is it going to be only these two? That is clear, because the even sequence and odd, even subsequence and odd subsequence partition the sequence nth root of an in two parts, right? So to say, so that when it, and those two parts are convergent, one of them is converging to root b, the other is converging to root a. So if you take any convergent subsequence of nth root of an, then it has to be consisting of all even terms after a certain term, or all odd terms after a certain term. Otherwise, it will not be convergent. This we have discussed earlier also. I just want to stress that point. That since a so-called partition you have been able to construct of the original sequence in two subsequences which are converging to two different limits, what you can conclude is that the only cluster points of nth root of an, this sequence, are going to be these 2 points, square root of b and square root of a. And therefore, its lim sup of the sequence nth root of an will be the maximum of these two. And since a is less than b, therefore, the lim sup is going to be square root of b. Now you have that b is less than 1, therefore square root of b is less than 1. Therefore, by root test, you can conclude that this series will actually converge. So this is an example where it shows why you should learn the result in its full generality, because here the limit will not exist, but it is the lim sup which is going to give you the information. Okay, so let us look at another example. Suppose you are given that series is summation n equal to 1 to infinity un, where again un is taking two different values dependent on whether n is even or odd. So for all even n, un is equal to 1 by 3 to the power n, and for all odd n, un is 5 to the power n. So again, if you want to find out what is lim sup of nth root of un, then what you have to do is, first of all, you have to see what is happening to nth root of un for various values of n, right? So you can easily observe, this is not a very difficult example, that when you take n to be even, then nth root of un, again un are positive, so we don't have to bother about writing mod. So nth root of un is going to be 1/3, right? Just n by n, so that becomes 1/3. And when n is odd, then it becomes 5, right? So what is your, again here, limit n tending to infinity, nth root of un will not exist. What exists is the lim sup of nth root of un, and which is equal to 5, right? So that 5 is since greater than 1. Therefore, by root test, you can say that the series diverges to infinity. Right? Okay. Another example which I want to talk about is interesting because it tells you that root test is in some sense stronger than ratio test. That is, there are situations where ratio test will give you no information, but you applying root test, you will get a conclusion. So let us look at this series. This series is what? Summation n equal to 1 to infinity an, where an is looking like this ugly number. So what is that number? 2 to the power minus n uh, minus 1 to the power n, right? So actually your a n is equal to what? It is equal to 1 divided by 2 to the power n times, so let me use a star for that. So times, this is minus, so it becomes a plus, right? So it becomes 2 to the power minus 1 to the power n. something like this. Is this all right? I think, can you understand this? It is 2 to the power minus n into 2 to the power minus of minus 1 to the power n. So this becomes an is equal to 1 by 2 to the power n times 2 to the power minus 1 to the power n. So what will this look like? This will look like, if you have your uh, so let me just write it here. So if you have n even, okay, so suppose n is even, then it looks like uh, 1 by 2 to the power n, that much is okay, that will not change, times 2 to the power minus 1 to the power n, right? So n is even, so it becomes minus 1 to the power n, even number becomes just 1. So this times 2, right? So this into 2, this is what your number is going to look like. So 1 by 2 to the power n into 2, so it looks like 1 by 2 to the power n minus 1, right? I am correct? I want to write a by here. So 1 by 2 to the power n minus 1. This is what it looks like when n is even. Even though it looks so ugly here, it is actually this number. And when n is odd, then what does it look like? Then it looks like 1 by 2 to the power n, you keep on repeating, times 2 to the power minus 1 to the power n. So that becomes what? That becomes n is odd now. So it is just minus 1. So 2 to the power minus 1 is what? Again, you have a half. So this becomes equal to 1 by 2 to the power n plus 1. I'm correct? Right? So when n is even, then it looks like half to the power n minus 1, and when n is odd, then it looks like half to the power n plus 1. So if you are just looking at the nth root of an, what will it become? It will become 1 by 2 to the power n minus 1 divided by n here, and here it will become 1 by 2 to the power n plus 1 by n, right? So n minus 1 divided by n, that so again, let me use this. So n minus 1 divided by n, this will converge, right? So I want to draw an arrow. Is it possible? I don't know. I can't see how to draw an arrow, but let me just write it down. So n minus 1. So what do I want to say is this. If you look at limit n tending to infinity, n minus 1 by n, this is going to be equal to 1. Not 1. How much? 1 minus 1 by n, right? So 1, yes. So this is going to be 1. Similarly, your limit n tending to infinity, here it becomes n plus 1. So n plus 1 divided by n, that is also going to be equal to 1. So what do you get when you look at your nth root, limit n tending to infinity, nth root of mod an, that is actually going to be equal to half, right? So it is easy after you look at this calculation. It is just 1 by 2 to the power n minus 1 when n is even, and 1 by 2 to the power n plus 1 when it is odd. So if you are looking at, the numbers look different when you have different values of n, but if you look at the subsequence consisting of only even terms, that converges to half, right? Because n minus 1 by n converges to 1. And similarly, if you look at the sequence consisting of only odd terms, then that also converges to half, because n plus 1 by n also converges to 1 as n tends to infinity. So in either of these two cases, even or odd, if you look at the subsequence consisting of nth root of an, that is going to be a convergent sequence and it converges to half. So therefore, the original sequence nth root of an will also converge, and that converges to half. So, and half is naturally less than 1. So by root test, you get that summation an converges, right? So I hope I have made myself clear. So now let us look at the next part. So what is the next part? That this particular series, when you look at it as from the ratio test viewpoint, you will not get any result. So let me just, instead of trying to write down and waste time, let us look at the calculation as written in the slide. Let us see if I can do it. So an plus 1 divided by an, this is what we have to calculate for our ratio test. So what is an plus 1? What is an first of all? An is 2 to the power minus n minus of minus 1 to the power n, right? So here instead of n you have to write down n plus 1. So you get 2 to the power minus of n plus 1. So that becomes n minus 1 minus minus 1 to the power n plus 1. Fine. And what is an? An is 2 to the power minus n minus minus 1 to the power n. Everything is a power of 2. Please note that. So this is what you get as n plus 1 divided by an. So what am I doing is that this 2 to the power minus n, I'm taking it to the top. So it becomes 2 to the power n here because it was 1 by an. Yeah, I'm correct. So this is 1 by 2 to the power n. So that will become the numerator here. And this will become the denominator. So 2 to the power n plus 1. So I'm ignoring the second part here and just writing down what do we get. So I get just 2 to the power n by 2 to the power n plus 1. And what is the second part? Let us write it separately. So for the second part you get 2 to the power minus of minus 1 to the power n. So that becomes 2 to the power minus 1 to the power n, right? And have I been correct here? Yeah. And this becomes minus of minus 1 to the power n plus 1. So I think I'm correct. If I write this as, this is just 2 to the power minus 1 to the power n here, right? So when it goes on the top, doesn't it become a negative? And this becomes, this goes in the bottom, right? So 2 to the power minus 1 to the power n plus 1. So am I correct? Let us just see. It's very difficult to write all these things now. Do it here itself. Oh, I'm sorry. So I have, let me use text, okay, that is easier. So I have 2 to the power, what? On the top I have minus 1 to the power n plus 1, right? And this is what is happening. I'm just looking at the second part. So this becomes minus of this, minus 1 to the power n plus 1. So it is actually minus 1 to the power n plus 2 here. And then I have at the bottom, I have in the denominator 2 to the power minus of minus 1 to the power n. So that becomes 2 to the power minus 1 to the power, sorry, to the power n plus 1, right? So let us just shift it a little bit on this side. So this is what, and let us get it below. So this is what it looks like. Let us see, 2 to the power minus 1 to the power n plus 2 divided by, I am correct, divided by 2 to the power minus 1 to the power n plus 1. So what is that going to be equal to? That is going to be equal to 2 to the power minus 1 to the power n plus 2 will just become minus 1 to the power n on the top, right? And this you have to divide by 2 to the power minus 1 to the power n plus 1. So it becomes to the power, let us write it like this, minus 1 to the power n minus n plus 1. This looks horrible, but let us see what it turns out to be. So that becomes equal to n minus n goes off, so all is remaining is minus 1. So it is 2 to the power minus 1 to the power minus 1. So it is just to the power minus 1. So that becomes just 2 to the power minus 1. So you get a half here. That is what I want to claim. That this guy is just half. And this is also 1 by, this is half is clear, right? And why is this half? Did I do it correctly or I did not do it correctly? This was minus 1 to the power n plus 1. That is all right. And this is minus of minus 1 to the power n. So it just goes on the top. So it becomes 2 to the power minus 1 to the power n. This is all right, no? Oh, okay, so why did I bother about all these things? Let us just clear it. See, I just have 2 to the power, so I'm making my life difficult unnecessarily. This is 2 to the power minus 1 to the power n plus 1. This is coming from here. And here it was 2 to the power minus of minus 1 to the power n. So it goes on the top as 2 to the power minus 1 to the power n. Now it is all right actually. So you get 2 to the power n divided by 2 to the power n plus 1, and you have this. So 2 to the power n divided by 2 to the power n plus 1 is half, and this becomes 2 to the power minus 1. If you take common, then you will get 1. So let me at least write this. So I have this thing. I'm looking at minus 1 to the power n. I'm taking that common. So if I take that common, I get 1 minus, and here you have minus 1 to the power n into minus 1. So if you just take minus 1 to the power n common, you get minus of minus 1 to the power 1. So you just get plus 1. I'm correct or not? You take out minus 1 to the power n, you get a 1 here, and then here you have minus of minus 1, so you get a plus 1 because you're taking out minus 1 to the power n. So actually you're left with minus of minus 1 here, right? This is what is happening. So that is equal to minus 1 to the power n times 1 minus minus 1 becomes 2, right? So this is what I'm trying to say. So this one becomes 2 to the power minus 1 into 2. This is, everything is in the power, and this is half. So now let us see. So what is this? This is actually equal to what? If you take n to be even, then it becomes equal to 2 when n is even, and what is it equal to when n is odd? Then it becomes minus 2 when n is odd, right? So what does this look like? Let us see. So if you have half into 2 to the power something, the power we are calculating here, right? So the power is 2 when n is even. So it becomes 2 squared, so 4 divided by 2, so it becomes 2 when n is even. And when n is odd, then this is becoming 2 to the power minus 2, right? So it becomes half into 1 by 2 square. So it becomes 1 by 2 cube. So n is odd. So whatever I have done here is I have calculated the power of 2 here. So power of 2 is going to be 2 when n is even. So that you get 2 square by 2. So that is 2 when n is even. And when n is odd, then it becomes 2 to the power minus 2. So it becomes half into 1 by 2 square. So it becomes 1 by 8, right? So what is the final conclusion? Conclusion is that if you look at an plus 1 by an, then every even term is actually going to be equal to 2 for this sequence. And every odd term is going to be equal to 1 by 8. So at least the sequence does not converge. Now, if you look at the lim sup of an plus 1 by an, that is 2, which is greater than 1. And if you look at the lim inf of an plus 1 by an, that is 1 by 8, which is less than 1. So you can make no conclusion using ratio test. Because if lim sup was less than 1, then you could have said that it is convergent. If lim sup was greater than 1, then you could, lim inf was greater than 1, then you could have said that it was divergent. But here the opposite thing is happening, right? Lim sup is becoming greater than 1 and lim inf is becoming less than 1. So that type of thing is not going to help you at all. And therefore, this particular sequence, uh, you will not be applied to, for this particular series, you will not be applied ratio test to get any information about its behavior as to convergence or divergence. This is what I want to do. There is some small calculation here, which I hope I have made it clear now for you, because I just step jumped here. Okay, so let us go on to the next step. Okay, so the next thing which I want to talk about is the Leibniz theorem, which says the following, that if you look at a monotone decreasing sequence of positive real numbers, so, which is a null sequence. Okay, so you have a monotone decreasing sequence of positive real numbers, which is such that its limit as n tends to infinity an equal to 0. Then if you consider the series a1 minus a2 plus a3 minus a4 plus etc., then this series is going to converge. Such a series is called an alternating series because every your ANs are all positive real numbers, notice. So what is happening is that the first term is positive, second term now becomes negative because we put a minus here. Third term is positive, fourth term is negative, and so on. So this particular series will converge. So even before going to the proof, let me just mention one thing here. In the very beginning of our discussion on series, we had decided that if a series converges, then if you multiply that series term by a scalar, then that particular series will also converge. So since this series converges, if you multiply by a minus 1, that will also converge. So it is not necessary that you have to start with a positive term, then a negative term, then a positive term, then a negative term to get a convergent series, provided the rest of the conditions are satisfied. It could be that you started with a negative term, then you got a positive term, negative term, positive term, and so on. That would also converge. That Leibniz theorem is ensuring it, provided the sequence AN is a monotone decreasing sequence. First of all, it should be a sequence of positive real numbers, so that whenever you write it like this, you do get an alternating series. The sign of the terms keep changing, and you should have that limit n tending to infinity AN is equal to 0. So you need these three conditions to say that Leibniz that the theorem is going to tell you that the series converges. Okay, so what we do is we call the nth term of this nth partial sum of this series to be Sn. So Sn will look like summation k is equal to 1 to n minus 1 to the power k minus 1 into ak, right? That is what we have. So what will we do now is that we will notice that if I look at all the even terms of the sequence of partial sums, then that is going to give you a monotone increasing sequence. So how will we notice that? You first of all look at S2n plus 2 minus S2n. This is for any n in n. So what does S2n look like? S2n looks like A1 minus A2 plus A3 minus A4 etc. till minus A2n. And S2n plus 2 will look like, S2n plus 2 will look like A1 minus A2 plus A3 minus A4 plus etc. plus A2n minus 1 minus A2n minus 2. So when you are writing S2n plus 2 minus S2n, you are subtracting the first 2n terms, right, of that particular series. So all you are left with A2n plus 1 minus A2n plus 2. Now, AN is a monotone decreasing sequence. So, A2n plus 1 minus A2n plus 2 is obviously going to be greater than equal to 0, because 2n plus 1th term of the sequence AN is greater than equal to 2n plus 2th term of the sequence. It is a monotone decreasing sequence. So, what do you get? You get that S2n plus 2 is greater than equal to S2n for all positive integers n. So therefore, S4 is greater than equal to S2, S6 is greater than equal to S4 and so on. So that what do you get? That S2n is a monotone increasing sequence. Not only that, if you look at any term like this, S2n, which is the 2nth partial sum of the original series, then it is what? It is A1 minus A2 plus A3 minus A4 plus A5 etc. till minus A2n minus 2 plus A2n minus 1 minus A2n. So since this is a finite sum, you can arrange it like this, that you can take the second and third term together and put a minus sign in front of it. So you get minus of A2 minus A3 minus A4 minus A5, right? It makes sense. All the odd ones have to have positive sign. So that is okay. And so on till the 2n minus 1th term. So you get minus A2n minus 2 minus A2n minus 1. So what is happening is that in the bracket A2 minus A3, this is going to be a negative number, right? Because, no, positive number. Because A2 is, AN is a monotone decreasing sequence. So you have A1 greater than equal to A2 greater than equal to A3 and so on. So A2 is greater than A3, A4 is greater than equal to, A5 and so on. So all things in this first bracket, they are all positive numbers. And A2n is a positive number because AN is a sequence of positive real numbers. So all these numbers in the bracket are positive numbers. A2n is also a positive number. So you are subtracting so many terms which are positive numbers from A1. Right? So you're subtracting A2 minus A3, which is positive, plus A4 minus A5, plus etc., plus A2n minus 2 minus A2n minus 1, plus A2n. This whole thing, which is a positive number, you're subtracting from A1. Therefore, what will you get is that a number which is less than or equal to A1. So S2n is always going to be less than or equal to A1. So S2n, that sequence of even terms of the sequence of partial sums of the given series, is a monotone increasing sequence and it is bounded above. So what do we know? That it converges. So let us say that it converges to L1. That is, suppose limit n tending to infinity S2n is equal to L1. Very good. Now what we will do? We will look at the odd terms of the sequence of partial sums. So again, we do the same calculation. We write down S2n plus 1 minus S2n minus 1. So from S2n plus 1, you are subtracting the S2n minus 1 means till the 2n minus 1th terms. So you are left out with what? You are left out with the 2nth term and the 2n plus 1th term. So 2nth term has a minus in front of it. So you are left with A2n plus 1 minus A2n. Again, AN is monotone decreasing. So A2n plus 1 is less than or equal to A2n, right? It keeps on decreasing. So therefore, A2n plus 1 minus A2n is less than or equal to 0. So what does that tell you? It tells you that S2n plus 1 is less than or equal to S2n minus 1. So if you start with say n equal to 1, then you have S3 is less than or equal to S1, S5 is less than or equal to S3 and so on, so that your S2n plus 1, it forms a monotone decreasing sequence. This is what it is telling here. And secondly, you want to say that it is bounded below. So how will you do that? You just write down what is S2n plus 1. That is A1 minus A2 plus A3 minus A4 plus etc. plus A2n minus 1 minus A2n plus A2n plus 1. The way we had, all the odd terms were positive and the even terms had a minus sign in front of them. Now you arrange it like this, right? You look at A1 minus A2 together, then you look at A3 minus A4 and so on, A2n minus 1 minus A2n. And you have one extra term, A2n plus 1. So what can you say about A1 minus A2? That is greater than equal to 0 because AN is monotone decreasing. So A1 minus A2 is greater than equal to 0, A3 minus A4 is greater than equal to 0 and so on. A2n minus 1 is greater than equal to A2n. And what do you know about A2n plus 1? A2n plus 1 is a positive real number. So what you are doing is you are adding positive numbers to the number A1 minus A2. Right? You should not take this one because that will depend on n. We don't want that. What we want is we want a lower bound and that lower bound should be independent of n. So you look at A1 minus A2. So this number is going to be greater than equal to A1 minus A2 because all you are doing is you are adding some non-negative numbers to it and this one is positive actually. So what do you get? You get that the odd terms of the sequence of partial sums of the given series form a bounded below monotone decreasing sequence. So therefore it will again be convergent. So let us call its limit L2. So we have seen that the even terms of the sequence of partial sums converges because it is bounded above monotone increasing and it converges to L1, and the odd terms also are a convergent sequence because they form a bounded below monotone decreasing sequence. And suppose its limit is L2. Then the first thing to observe is that L2 is going to be equal to L1. Why? Because if you look at S2n plus 1 minus S2n, then all you're left out with is A2n plus 1. S2n plus 1 is you keep on adding A1 minus A2 plus A3 minus A4, etc. till minus A2n plus A2n plus 1. And S2n is what? S2n is A1 minus A2 plus etc. You go till minus of A2n. So if you subtract S2n from S2n plus 1, only thing which is left out is the 2n plus 1th term. So if now this sequence converges, this sequence converges. So if you take the limit as n tends to infinity, it will converge to L1 minus L2, right? This was let me see. It converges to L2 minus L1. This is converging to L2, this is converging to L1. So it converges to L2 minus L1. So therefore, if you look at all the odd terms of this original sequence, that is also convergent actually, and it converges to limit n tending to infinity. It converges to L2 minus L1. So I have been slightly fast here. So if you liked, you could have done one more step. This is telling you that A2n plus 1 converges. Oh, I'm sorry. I'm very sorry. We see that this converges to L2 minus L1, and actually I was forgetting. We have one thing in hand. We have that our original sequence AN is also a null sequence. So we know that limit n tending to infinity AN is 0. So since limit n tending to infinity AN is 0, therefore limit n tending to infinity A2n plus 1 will also be 0. We have seen this, right? If a sequence converges, every subsequence of it converges and converges to the same limit. So what will happen is that L2 minus L1 will actually be equal to 0. So L1 is equal to L2. Now, what was L1 and L2? L1 was the sequence of, L1 was the limit of the sequence of the even terms, right, of partial sums. And L2 was the limit of the subsequence of the consisting of the odd terms. And since both of them are converging to the same limit, since L1 is equal to L2, this also we saw that this implies that limit n tending to infinity Sn is equal to L, right? And this is by definition the meaning of the concept that this series summation n equal to 1 to infinity minus 1 to the power n minus 1 an converges, because this is the sequence of its partial sums. What would have happened if you had just multiplied by minus 1 is that your whatever is becoming monotone increasing bounded above would have become monotone decreasing bounded below, and the vice versa, right? So the only thing which would change is the argument here, that would become different, but you would still get the rest of the philosophy of the proof would remain the same. Okay. So this is our Leibniz theorem. And the final topic in this chapter is the absolute convergence. In absolute convergence, we are not going to discuss many things. We just uh, give you an idea, that's all, and we will stop. So what is the meaning of absolute convergence? That if you are given a series summation k equal to 1 to infinity ak, and suppose that when I look at modulus of this, then the series which I get, summation k equal to 1 to infinity mod ak, suppose that particular series converges, then you say that the original series is absolutely convergent. Take the absolute value of each of its terms. If the resultant series converges, then the original series is said to be absolutely convergent. If the original series converges, so here we are not saying that the original series should converge beforehand, nothing like that. We are just saying, suppose you are given a series in hand, and when you are applying modulus to each of its term, then the resultant series is convergent. If this happens, then you will say that the original series is absolutely convergent. And on the other hand, if you have a series where the original series itself converged, but after putting the modulus, you see that it does not converge, then you say that this original series is a conditionally convergent series. All right. So let us look at one major theorem in this, which says that if you have an absolutely convergent series, then it is bound to be a convergent series, right? So therefore, even if you did not mention it beforehand, it happens that if you have an absolutely convergent series, then it will automatically be convergent. So what is the proof of that? Proof is straightforward using Cauchy's criterion. So suppose I take any epsilon greater than 0. We are given that the series summation k equal to 1 to infinity mod ak converges. So therefore, dependent on this epsilon, I will be able to get a positive integer n, so that for all little m greater than equal to n greater than equal to capital N, summation k equal to n to m mod ak will be less than epsilon. I'm just writing down the Cauchy's criterion. I don't have to write mod now because these are all non-negative numbers, right? So this is true by Cauchy's criterion because summation mod ak converges. Now, what do you know about modulus of summation k equal to n to m ak? If you apply triangle inequality, then this is less than or equal to summation k is equal to n to m mod ak, right? So if you choose your m and n so that m is greater than equal to n is greater than equal to capital N, then since this is less than epsilon, this modulus of this sum will automatically become less than epsilon. So as trivial as that, by Cauchy's criterion, you conclude that the original series summation ak is also convergent. So if a series is absolutely convergent, original series is convergent. This is what we have proved, and we will just see an example where the converse is not true, and we will stop. Let me tell you that this is just the tip of the iceberg. There are lots of nice things happening if you have an absolutely convergent series, but maybe in some later on in a different course we will be able to discuss things about it. So what is the counter example? Just look at this series summation n equal to 1 to infinity minus 1 to the power n minus 1 by n. So this is tailor made to apply Leibniz test, right? You have this series whose terms, first you look at the sequence 1 by n. The sequence 1 by n is a very nice sequence in the sense it is monotone decreasing, and it is a null sequence consisting of all positive terms. So your basic conditions of Leibniz theorem are all satisfied, and then you are looking at this alternating series. It is starting from 1, then it is minus half plus 1/3 minus 1/4 and so on. So this series is going to converge by Leibniz theorem, which you saw just now. But if you put a modulus here, then what do you get? You get the harmonic series, summation n equal to 1 to infinity 1 by n. And that series is not convergent. We have seen it, right? So this particular series is an example of a conditionally convergent series, which is not absolutely convergent. So I have completed the 95% of your syllabus, or 99% you can say. There is only one little bit left out, which is, okay, so since we are mathematicians, let me just correct it a little bit, maybe 97%. What is left out is compact sets. And that I will discuss. And from the next week, I hope to start core 5, and we will make our decisions about how to conduct those classes. Okay, so I will stop here.